Hi, hello students. Welcome back to India's most comprehensive online learning platform, BYJU'S Exam Prep. This is Anil Prasad Purampudi, and in this session, we are going to discuss about the important topics of the operating system that are expected in BARC 2024. Yesterday, we already started this, in which we covered some important topics. Now, through some practice questions, we'll understand all the important concepts that are expected in GATE 2024. So let us start our session without having no delay whatsoever. To start with, this is about myself. As you already knew, this is Anil Prasad Purampudi. I'm a triple PG holder. I did my MS in Information Technology, MBA. I also did my MSc in Mathematics. And for the past 13 plus years, I've been training the students in GATE and various competitive exams. And I trained students across all over India, including Andaman and Nicobar and Srinagar. For the past 5 plus years, I've been guiding the students towards their career. More than 1,000 seminars I just have conducted and organized. When it comes to my expertise, I'm expert in the computer architecture, operating systems, data structures, compiler design, and verbal ability. So let us start this session. And an important announcement to be made, that is, Byjus is offering 90% scholarship through a scholarship test, which is going to be conducted and organized on 10th March in between 9 a.m. to 9 p.m. If you take this test and if you can crack this test, you will be given up to 90% scholarship in your course fees. So do not miss this wonderful opportunity. Take this test and get this as much as possible. Based on your score, you will be getting up to, imagine, 90% of your entire fee, okay, as a scholarship. So do not miss this. You just get enrolled as quickly as possible and attend to this test and get 90% scholarship. And one more important announcement, that is, I just myself am taking a seminar and a workshop on preparation strategy to crack GATE 2025 in one shot. Because when you prepare for the GATE exam, if you are not guided and if you are not mentored properly, that will go in vain. Most of the people, they will not be able to crack the GATE exam in the first attempt. Hi Atreya, very good evening. Good to see you back. Yeah. So to get back to my announcement, we have a seminar and a hands-on session and a workshop which is coming in your way, which is being taken by myself on how to crack the GATE exam in one attempt in the first shot. Because most of the people, although they prepare well, they will not be able to crack the GATE exam because of the misdirection or misguidance. So do not worry about it, because I just am coming with a wonderful session of how to crack the GATE exam in one shot, in which I just am going to give you all the possible tips and tricks and how you can lay out your proper path and strategy towards your preparation in preparing for the GATE 2025 or 2026. Whenever you're appearing, how to prepare, how to crack the GATE exam in one shot. So register now, which this live is coming on 13 March and 7:30 a.m. And do not miss this opportunity. And we also started one ground zero series, as I've been discussing, as I've been talking about the basics of a student who actually is aspiring the GATE exam. First of all, if you are aspiring for the GATE exam, you just need to understand that you need to have your basics perfect. You must have your basics top notch, for which we have actually been coming up with a solution, with an initiative, that is that is just a minute, there is a technical glitch. I'll just get back to you. There's a technical glitch. Just give me 2 minutes. 2 minutes, I'll just get back. Just a minute. Give me 2 minutes. I'll be right back. I'll be right back into the session. Am I completely audible and visible? First of all, everyone should confirm so that I will go ahead. Am I completely audible and visible? Atresh Chaudhary, do you have you experience any lag in my voice or picture? Completely, right? Okay. Yep. Just give me 2 more minutes. Just I'm coming back. Yeah. Okay. Yeah. To address the problem of your basics, actually, just we have an initiative which is coming in your way. Have been coming in your way to have your basics right. Actually, we finished. I started with the computer architecture. Now operating system is going on. It's just not these two topics. We've been coming with every topic in which, first of all, we will target on your basics. We will have your basics right. So do not miss this session. So let us start with this now. As we already did some work in the yesterday's session, now through some practice questions, we'll completely have a complete idea how you will be able to crack the BARC exam through some important questions, so that you will be able to understand topics as well as the questions. The first question is on your way. Can somebody answer this question? Can somebody answer this question? The question is, what is the maximum number of processes that can be in the ready queue, ready state for a computer system with n CPUs? The question is, what is the maximum number of processes that can be in the ready queue or ready state for a computer system with n CPUs? The question I will explain you furthermore. That is, there is a computer system with several CPUs. Yes, Atresh Chaudhary, you are correct. There are several CPUs, and if it is a multi-processor system, it will be connected with one memory unit. Okay, the question is simple. In a multi-processor system, in the main memory, within the main memory, how many processes can be residing? This is the question. Here, you need to understand there is no relationship in between the number of processors in a multi-processor system and the number of processes that can reside within the memory. The number of processes within the main memory that can be residing is decided by something called the virtual memory. The number of processes, the degree of the multi-programming will be decided by the virtual memory of the system. And also there are other parameters contributing towards this, but the number of CPUs can never be a factor in deciding what is the total number of processes that can be kept in the main memory. Okay, are we done with this? Atresh Chaudhary, can you go to the next question? Yeah. The next question is, a process executes the code fork, fork, fork. Now, could somebody please tell me what is the total number of child process created by this fork, fork, fork? The fork is being executed for 3 times. You already knew that whenever fork process is a process executing a fork system call, whenever a process executing a fork system call, a child process is going to get created. If I'm a parent process, when I call a fork system call, what will happen? A child process gets created. When a child process gets created, obviously it will be the only process that created if the fork is called only for once. But here the fork is being called thrice simultaneously. one after another. It is something similar to the fork is being repeated for thrice in a loop. Now, Atreya Chaudhary, you are spot on, you are perfect. 7 is the correct answer. The total number of child processes that can be created when the fork is being executed in a loop is equal to 2 power n minus 1. Okay, what is this n? If there are n power process, the number of 2 power n minus 1 child process, that absolutely that you're correct. Yes, 2 power n minus 1, where n is the total number of times that the fork is being called or the loop is being repeated. I hope you got a point, right? Yes, the total number of child process that gets created is equal to 2 power 3, which is equal to 8 minus 1, which is equal to 7. Let us go to the next question. Are we done, everyone? I hope we are. Shall we go to the next question? Okay, fine. Now, consider the following code fragment. Again, this is related to the process creation. The operations on the process. Again, we do have a fork system call. What is a fork system call? When the fork system call gets executed, a child process gets created. Now, based on this, we need to solve this question. Consider the following code fragment. If fork is equal to 0, just a minute. If the fork, consider the following code fragment. If the fork is equal to 0, then what happens? This line will get executed. If the fork doesn't return 0, what will happen? The second line gets executed. So in this regard, what is correct? The question is, let u, v be the values printed by the parent process and x and y are the values printed by the child process. Now with respect to this, which is the correct answer? The first one is u is equal to x plus 10 and v is equal to y. B is u is equal to x plus 10 and v is not equal to y. And C is u plus 10 is equal to x and v is equal to y. And D, u plus 10 is equal to x and v is not equal to y. Now here we just need to understand a few things that are related to the fork system call. Now the thing is, whenever a parent process calls a fork system call, what exactly is going to happen? This fork system call, it is not hard. If you just can focus and concentrate on what I am talking about, you will be able to solve any questions on operations and process. So for which I want you people to completely focus on what I am telling. Okay, this is very, very fundamental question, very easy question. But if you do not listen to this, it may get harder. So understand this. Okay, let us say there is a parent process. I'm a parent process. Okay, Anil is a parent process. Now I'm executing a fork system call. What is my intention behind this calling this fork system call? To create a child process. Okay, now understand this fork. Let us say the child that is being created during the fork is, let us say, ATR Atreya is the child that is going to get created. Okay, if the fork is successful, then a child Atreya will get created. But there are several factors to be considered at this point. Fork is a system call. Fork is a function, right? Yes or no? Now the thing is, when the fork is called, the fork function can return three possible values. What are those? A fork can return 0, or a fork can return 1, or a fork can return a negative value. Let us say -1. Fork, every time when the fork is called, it will have three possible outcomes. One is 0, second one is 1, third one is a negative value. Now here the negative value is completely ruled out. When the fork returns a negative value, that means the child creation is not successful, is said to be not, child creation is failed. So this is out of question. Now what is it with this? What is it with this fork returns 0, fork returns 1? In both cases, if it is a non-negative value, either it is a 0 or 1, the child creation is successful. Okay, when the fork returns 0, then that means the child creation is completely successful. Okay, but what is the difference? Simple. When fork returns 0, child creation is successful and child is right now executing. Okay, who is created? Atreya is created. Atreya is the child to the system Anil. Okay, Vangalpudi, Chandrasekhar, C. C is the correct answer. Yes. C is the correct answer. Anyhow, I'll tell you why the C is the correct answer. Now, when fork, the parent Anil, he calls a fork system call, and if it returns 0, then now what happening is the child R3 gets created. Now R3 is executing in the CPU, sending Anil back to the main memory. Simple. When the fork returns 0, child is created and child is now executing. If fork returns 1, if fork returns 0, meaning child is executing. 1 meaning child is created but still parent is executing. In both cases, child creation is successful, but when it comes to the 0, child is executing, but when it comes to the 1, parent is executing. I hope you got the point. Now, what does it mean? When fork returns 0, this fragment of the code is being executed by the child. This fragment of the code is being executed by the parent. When fork returns 0, child is executing. So when child executes, this statement is executing, meaning this statement is being executed by the child and this statement is being executed by the parent. You got the point? I hope so. Now the thing is, what is this? What child executes? Child says A is equal to A plus 5. Parent says A is equal to A minus 5. Okay, for an example, when A is equal to, when A is equal to 5, child will make A is equal to 5 plus 5 is equal to 10. Okay, parent says A is equal to A minus 5, which is equal to 0. Okay, now what is the difference between parent and child? Child is parent plus 10, right? So here the thing is, what is this? U and V values printed by the parent process, and X and Y values that are the values that are printed by the child process. Now, X is equal to U plus 10. X is the child value, U plus 10. U is equal to parent value plus 10, right? What is the difference between parent and child? Child is equal to parent plus 10, where U is the parent value plus 10 is equal to X. Now the thing is, understand carefully. When this is being printed, two values are being printed. The first one is either both parent or child, when they are executing the statements, they are initially printing the value of A and also the address of A. Here also value of A, address of A. Here this is X, this is U. Okay. Now the thing is, anyhow, U plus 10 is equal to X. We just have to come to the conclusion. Hi Neha Maurya, very good evening. But understand, when it comes to the address, me and my child are expected to be residing in the same space of the main memory. My space in the main memory and my child space in the main memory will be one and the same. That means both parent child will be printing the same address. So here C is the correct answer. Are we clear, Maurya, Neha, or Vainikunta? Already Vainikunta, this Vangalapudi K Vainikunta, he already told me the answer. Are we clear? Did you understand this? Can I go to the next question? Or you want me to repeat it here? Any doubts? Okay then, let me go to the next question. Now, I want you people, it's a simple question. It is expected again, and because there are a lot of things, diagrammatical questions are asked in the previous years of the BARC. So this is one of such questions that you are expected this time. So the thing is, the process state transition diagram in below figure is the representative of what? A batch operating system, an operating system with a preemptive scheduler, an operating system with a non-preemptive scheduler, a uniprogrammed operating system. May I know what operating system is being represented by this diagram? State transition diagram. Atreya, Neha, or Vangalpudi, whoever you are, I want you people to answer this. Okay. B. Answer B. An operating system with a preemptive scheduler. What about Neha? Yes. Simple. There is nothing much to talk about it because here, understand carefully. The possible state transitions are, a process will be moving from new to the ready state. Okay, that is, the process is just created. New meaning just created. Okay, after just created, it will occupy the memory space. When it is in the main memory, it is said to be in the ready state. Right after it is in the memory, some time later it will get transferred to the CPU for execution. Okay, when a process is in the CPU, there are only two legal states. If I am in the CPU, there are only two possible states legally that I can enter into, rather positively that I can enter into. One is to the blocked state, meaning whenever I am performing an IO operation, I will be temporarily blocked from execution. Or when I completely got executed, I will be terminated. These are the only two states possibly that I can enter by myself. Okay, but you just can also see there is an arrow from running state to the ready state. Whenever there is an arrow from the running state to the ready state, it is just because of the interrupts. Okay, every system that enables the interrupt will associate with the will also enable the feature of the preemption, meaning if I am already in the CPU and there comes one more process in the ready queue, for example, A is executing in the CPU, there comes one more process B into the ready queue. Now what if B has got more priority than A? Obviously B will interrupt and preempt A. So A will go back to the ready state, B will enter into the running state. So this operating system is an operating system with a preemptive scheduler. No sound? Is my voice audible, Binu? I mean, several people saying that my voice. I hope I'm audible, Binu. There's no problem, I guess so. Am I completely audible and visible? Yep. How about other people, Vangalapudi and Neha? Yes. So let me go to the next question. Shall we go to the next question? I guess we can. Now, the next question is, next question is as follows this. The time taken to switch between the user to the kernel modes of the execution be T1, while the time taken to switch between two processes be T2. Which of the following is true? T1 is greater than T2, T1 is equal to T2, T1 is less than T2. And the fourth option is, nothing can be said about the relationship between T1 and T2. What may be your answer? The thing is, you know already that the CPU is executing in two modes. One is user mode and one more is kernel mode. Okay, user mode and a kernel mode. Now, what exactly is it with this user mode and a kernel mode? Understand carefully. I will take an example of your C program. In your C program, you might have written several statements. After that statement, you have written a printf statement. Okay. Now understand, printf is going to initiate a service of the operating system. Printf is going to initiate Chandu, I guess I am. Vaikuntha, am I audible? Just a minute. Very good. So you just check your audio cable and whatever. Let me get back to this. Okay, fine. From my side, everything is clear. Now thing is, yeah, there is user mode, there is a kernel mode. For an example, int a is equal to 10. Int sorry, let me make it clear. There is one instruction, int a is equal to 10, a is equal to a plus 10, and I would say printf a. I just am not writing the complete syntax, but you need to imagine that after two instructions, there is one instruction which is called printf a. Now understand this. Listen. I will explain. You just need to hold your horses for a while. I'm going to give you one important thing to remember for all the time. See, whenever printf statement is being executed, it is going to initiate one system call, rather service of the operating system, because By using the printf statement, we are going to access an IO device. Every time when you are accessing an IO device, that is just nothing but a service. The service can never directly be accessed by the user. Rather, it will be given, the service will be accessed by the kernel mode. Understand? In the simple statements, these two instructions will be executed in the user mode. Just a minute. A is equal to 10. A is equal to A plus 10. These two will be executed in the user mode. But there is something called printf. There is something called printf. Printf A. A is equal to 10. Again, A is equal to A plus 10. These two will get executed in the user mode. This will be executed in the kernel mode. Now, what we actually require is, in order to switch the mode from the user to kernel, we require a software interrupt. What is the job of the software interrupt? The software interrupt will change the mode from the user mode to the kernel mode. Whenever the mode switch is happening, where exactly, how exactly it's going to happen? The mode switch. Are you listening? Gate 1 mark questions are enough or not for the practice? See, you just cannot simply rely on 1 mark questions. Sometimes in the BARC, when you look at the previous year's questions, there also the 2 mark questions asked as a single statement. So it's just not quite adequate, I would say. You also need to go through some important questions in gate. It's just I request you not to target only 1 mark questions. Okay, you got me? Yep. Now when the mode switch is happening, just a minute. The question is which modes, I just missed this question again. User to kernel modes of the execution T1 and the time taken to switch between two processes is T2. Yes. Okay. The thing is, when the processes are being switched, one process is going inside, one more process is going outside. Process switch includes the mode switch. Write it down somewhere. A process P1 is executing, process P2 is waiting. Now it is the time to switch this process. P1 is getting out, P2 is coming in. Process switch will also include the mode switch. Mode switch doesn't include the process switch. Okay. Now with respect to this statement, what is correct? Okay, here mode switch meaning user to kernel mode. This is an example. Now with respect to my statements, based on my statements, what exactly is correct? Is T1 is greater than T2? T1 is equal to T2? T1 is less than T2? What? What exactly is correct in this regard? What? Here T1 is the mode switch is less than T2. T2 is the process switch because process switch also includes the mode switch. Write it down somewhere. Process switch also includes the mode switch. Hope you got a point. So let me write it down here. Process switch includes mode switch. Okay, that makes T2 greater than T1. Okay, so am I clear? Can I go to the next question? Atreya? Yeah, this is already explained, discussed. Now, there comes the next question. Sir, is equal time required for the switching from the user to kernel mode or under reverse? Let me talk about this. Just what? Sir, is equal time required for switching from user to kernel mode and reverse? Meaning user to kernel and kernel to user, right? No. Listen. From user to kernel, more time. And from kernel to user, less time. Sir, why? Can you substantiate? Of course I would, because in order to switch the mode in between user and kernel, from the user to kernel, I require a software interrupt. A software interrupt will get triggered. That software interrupt is responsible for switching the mode from the user to kernel, which takes some time, which consumes some time. But to change the mode from kernel to user, I don't require any software interrupt. To change the mode in between kernel to user, I don't require software interrupt at all. So obviously, the mode switch from the user to kernel will take a little more time than the mode switch from kernel to user. I hope you understood this. Okay. And the next question on your screen. May I have your answer for this question? Consider three processes P1, P2, P3 as shown in the table. Okay, process P1, process P2, process P3. The arrival time of process P1 is equal to 0. The arrival time of the process P2 is equal to 1, and arrival time with respect to process P3 is equal to 3. And the time units that are required by these three processes are 5, 7 and 4 respectively for P1, P2 and P3. Okay, so this is arrival time and the execution time required for process P1, P2, P3. And the question is, what is the completion order of these processes with respect to two scheduling algorithms? The first one is round robin, first one is FCFS, second one is round robin. Now, if you use FCFS, first come first serve scheduling algorithm, what is the order of the execution of these processes? If you use round robin with 2 units, what is the order of the execution? Any answers for this question? Any answers for this question? Okay, I'll explain. Stay focused. You just can practice later, but since it just may take some time, I'll let you know. Okay. Now, FCFS always will execute the processes according to their arrival time, right? So that is, P1 will execute first because P1 arrives into the main memory as the first guy. Of course, he will get executed first, followed by the P2, followed by the P3, because this is the arrival order of the process. In the arrival order, process will also finish and leave the system in FCFS. Okay, so FCFS always P1, P2, P3. So I will write here FCFS always is P1, P2 and P3. Okay. Now the thing is, what about round robin? Round robin with 2 unit time quantum. Every process can get into the CPU, but only is allowed to execute only for 2 time units. After 2 time units, the process is expected to be preempted with respect to this. Which is the correct answer? Let me tell you. See, most of the people, they confuse. Most of the people, they will jump into the trap that has actually been set for them. They will say even FCFS, round robin also is a refined FCFS, right? So both round robin and FCFS will go hand in hand. Round robin, if the round robin is P1, P2, P3, FCFS also is P1, P2, P3. There is no difference, but there is a difference. There is some catch in the question that you need to identify. I will tell you, I will show you right now. Let us say this is main memory. Okay. In the main memory, for all the processes, there is a ready queue maintained. Okay. What is the queue? Queue is the first in, first out, right? Now, let us say this is the ready queue of the main memory. Okay. Now, let us say this is the CPU. Understand this very carefully. At time 0, P1 arrived and will be appended into the beginning of the ready queue. Okay. Now at time 0, what happens? Immediately P1 will get transferred to the CPU for execution. Now P1 is not in the ready queue, rather it is already executing, right? Now at what time P1 will get preempted? At what time P1 will get preempted? After 2 clock cycle, the P1 will get preempted. But after the first clock cycle, P2 arrived into the ready queue, because since the ready queue is completely empty, P2 will occupy the first slot of the ready queue. There is nobody in the ready queue. The guy who already entered the ready queue get into the CPU because he is the only process that arrived as the first guy. Now when P1 is executing, after the first clock cycle, P2 already entered, occupied the first slot of the ready queue. Did you get me? Now the thing is, after the second clock cycle, what will happen? P3 did not come at all. After the second clock pulse, what will happen? P1 will leave. Did you get me? P1 will leave from the CPU to the main memory, and P2 will enter from the main memory to the CPU. After the second clock pulse, what will happen is P1 will go back to the main memory and occupy the first slot, because after the second clock pulse, P3 did not enter. And the guy who is actually awaiting in the ready queue will make his way into the CPU. Did you get me? After the second clock pulse, this is the snapshot of the system. Okay. And of course, Vanikunta, yes, he is correct. Now the thing is, after the second clock pulse, P2 is executing, P1 is awaiting in the first slot of the main memory. Now after third clock pulse, P3 entered into the ready queue. Now after which, this is the order. Then P2 gets into the CPU. Okay, then P1 goes. So the order of the execution will be P1 followed by P3 followed by P2. Clear? Okay, P2, P3, P1. Just a minute. Yeah, P1, P3, P2. It is not P1, P2, P3. Are we clear? So this is how the processes arrived into the main memory, and this is the completion order, that is P1, P3, P2. Can I go to the next question? Yes. The next question also is a simple question, but it just tricks your mind for some time. Let me tell you this. A scheduling algorithm assigns priority proportional to the waiting time of a process. What exactly is? See, I am giving you this question. What is the answer for this? What is the answer for this? What is the answer for this? If the waiting time is high, yes, Atreya, you are correct. If the waiting time is high, priority also is high. What you told is right. Now, according to this, what is the correct answer? What is this evaluating to? Where is Binu or Vangalpudi? Neha? Could you please let me know? I'll tell you, you don't need to think too much about it. There is something which should attract your eyes directly straight away. That is, the scheduler re-evaluates the priorities every t time units. We don't need to go for any other thing at all. Every t time units, and decide the next process to schedule. Okay, here t is the time quantum that has actually been assigned. Okay, so now when you look at the question, no, it's not shortest time remaining. Listen, you're missing a point. Okay, I will put it this way. There are process A, there are process B, there is a process A, B, C. Okay, process A, B, C. Now, every process starts with the priority 0. All the processes will start with the priority 0. Process A is priority 0, B is priority 0, C is priority 0. Okay, and all the processes arrive at time 0. All the process A, B, C arrived at a time 0. Okay, now every process starts with the priority 0. The scheduler re-evaluates the process priorities every t time units. Now let us say t is equal to 2. Okay, after every t time units, 2 time units, the scheduler will re-evaluate a priority. How? More the waiting time, more the priority, less the waiting time, less the priority. Now let us see. Initially, all the process will have the same, of course, yes, it is B, it is round robin, simple t time units. In which algorithm stipulated time frame will be given? There is only one algorithm in which a stipulated time frame will be given to the process, that is round robin. Now let me tell you this. Let us take A. Initially A, B, C all are having equal priorities, so there is no higher prioritized process. So what I will do is I will pick up A. Okay, A has been sent into the CPU. Very good, not a big deal. Now the thing is, A will be pulled back from the system after 2 clock cycles. After 2 clock cycles, there are 2 priorities. A just returned, meaning it is not waiting for any time at all, but B and C are actually waiting for 2 time units. Okay, so now there are 2 priorities, A with the least priority, B with the highest priority. B and C with the highest priority. So from the highest priority, again I will pick up one more process, I will send. Now B will execute. When B executes, it's only can execute for 2 milliseconds or 2 time units, after which this B also will come back. When B comes back, there are 3 priorities. C actually at that time waiting for 4 milliseconds, A is actually waiting for 2 milliseconds, B just which has come out right now, not waiting for any milliseconds. So C will be given first, A will be second, and B will be the third. So if the process iterates, it will become round robin, right? So this is what the answer for this round robin scheduling algorithm is, the algorithm that is given in the question. Let me go to the next question. Which scheduling policy is most suitable for a time shared operating system? Time shared operating system meaning what? If it is a time shared operating system, which scheduling algorithm is suitable? Is it SJF, round robin, FCFS, or none of the above? Understand this. The operating system we are using right now are time shared operating system. What is the time shared operating system? In the time shared operating system, user will get an illusion that multiple programs are being executed simultaneously. No, but it is not simultaneous execution. It is the concurrent execution. How concurrency can happen? Let us say there are 100 processes executing. All the 100 processes will execute concurrently. How? A process will execute for some time, immediately it will get printed. One more process will execute for some time, immediately will get printed after a stipulated time. So here, understand, if it is a time shared, always there is one possible algorithm that can be implemented on such operating system, which is round robin scheduling algorithm. Clear? Let's go to the next question. Which one of the statements are true? Shortest remaining time for scheduling may cause starvation is the first statement. Shortest remaining for scheduling may cause starvation. Second statement. Third statement is round robin is better than FCFS in terms of the response time. Which is the correct option? Which is the correct option? D? Yes, it is, because understand, shortest remaining time first or short. Okay, first 2 statements are equal, right? Okay, first one is SJF, second one is SRTF. But anyhow, option D is correct, because either it is SJF or it is SRTF. These are actually priority based algorithms. In the first case, shortest job process will be the process with the shortest time will be given the priority. In the second case, the process with the shortest remaining time will be given the priority. But understand, no matter what, if the algorithm is priority based, then there will definitely be a starvation. If the scheduling algorithm is a prioritized scheduling algorithm, priority based scheduling algorithm, priorities always leads to starvation. So this will lead to starvation, this also will lead to the starvation. Okay, both statements are correct. Round robin is better than FCFS in every aspect. It's just not the response time. It is better than round robin, always is better than the FCFS algorithm in every aspect. So option 1, 2, 3 all are correct. Next question. Now let us get into the most beautiful part of the operating system, synchronization. Okay, the first question. Consider the methods used by the process P1, P2 for accessing their critical sections whenever they need it, as given below. The initial values of the shared Boolean variables S1 and S2 are randomly assigned. Okay, what is S1 and S2? S1 and S2 are Boolean variables. Boolean variables meaning they can only possibly take either true or false. Here the question is, here in the statement what is given? S1 and S2 are randomly assigned. So take any values for S1 and S2. I will take S1 is equal to true and S2 also is equal to true. Randomly I am taking both are true, meaning both are equal. So with respect to this process P1 and P2, are executing. If they are executing, what are the which one of the following statements describes the properties achieved? Understand carefully. When you have a critical section, in order to protect the critical section, the solution must satisfy three criteria: mutual exclusion, bounded waiting, and the progress. What is mutual exclusion? In the critical section, only one process should be allowed. More than one process is not allowed into the critical section. What is bounded waiting? A process cannot re-enter into the critical section again and again while the other process actually is waiting. Third one is progress. If no process is actually in the critical section and one or some other process are waiting, those waiting process should enter into the critical section without delay. This is bounded waiting, mutual exclusion, and progress. With respect to this, what actually are achieved? While S1 is equal to S2, process P1 will get caught in the infinite while loop. While S1 is not equal to S2, process P2 will get caught in the while loop. Okay, let us have a look at this. Now S1, S2, I am saying both are equal. If both are equal, what is going to happen? The process P1 will not be able to enter into the critical section because it will get caught in the infinite while loop. Now let us say process P2 wants to enter into the critical section. Of course, it will be able to do so because it will get caught in the infinite while loop only when S1 is not equal to S2. Here there is no question about it because S1 and S2 are equal. So the process P2 can enter into the critical section. After which, what it does, it actually set S2 is not equal to S1. So then let us say S1 is equal to false, S2 is equal to true. Now when both S1 and S2 both and S1 and S2 are not equal, which process can enter into the critical section? Only process P1 can enter, process P2 cannot enter into the critical section. Now, which is actually achieved, which is actually not achieved? As Vangalpudi says, option A is correct. Mutual exclusion is guaranteed, but progress is not guaranteed at all. Why? Because, understand, let us say initially when S1 is equal to true, S2 also is equal to true, process P2 wants to enter into the critical section, it will be able to do so. But after coming out, process P2 sets S2 is equal to false, S1 is equal to false, S2 is equal to true. Now both are not equal, right? When both are not equal, will process P2 be able to enter into the critical section? No, it cannot. Who can enter? Only process P1 can enter into the critical section. Now understand a scenario where process P1 never wants to enter into the critical section. Never. In its total execution, process P1 never wants to enter into the critical section. But after some time, process P2 wants to re-enter into the critical section. Will it be able to do so? No. When process P2 can enter into the critical section? Only after process P1 enters into the critical section and sets S1 is equal to S2. When S1 is equal to S2, then only the process P2 will be able to enter into the critical section. Now, this condition violates progress. A process wants to enter into the critical section, but it will not be able to do so even though the other process doesn't want to enter. I hope I did make it myself very, very clear. Did you get it or not? Atrey Chaudhary and Mangalpudi K. How should I call you? Just, it's a long name. How should I call you? T. Vanikunta? Chakradhar. Okay, Chakradhar is fine, I guess. So did you understand this? All of you guys. Can you go to the next question? Or you want me to repeat again this? Can I? You people are there or not? Audible or not? Fine. I guess I just am taking this as. The next thing is, a critical region is a one which is enclosed by a pair of P1, P and V operations and semaphores. A program segment that has not been proven bug free. And the next thing is a program segment that often causes unexpected system crashes. Okay then, fine. A program segment where shared resources are accessed. Which is the correct answer for this? Where is Atrey Chaudhary and Neha? What's the answer for this? Chakradhar, Atrey Chaudhary, Neha, what is the answer for this? A. A program which is P and V operations. No, Chakradhar is not A. Understand? Critical region is a program segment where shared resources are accessed. C. Option A. Why I should reload option A? If there is a critical section, this must be protected by using some or the other locks. Here, P and V operations are belonging to semaphores. P and V operations, just you only can find it in the semaphores. Okay. So, there is no guarantee that all the critical section will be protected by the semaphore. There is no, because critical section can be protected by the locks or semaphores. The decision is yours. When you write an application, how you are going to protect your critical section in a piece of code, that will definitely be on you. That will be entirely on you. Either you use the semaphore or you don't use the semaphore, is completely on you. But if you use the semaphore, this critical section will be protected by P and V operations. But we don't know how the critical section is being protected. So it is not just P and V operations of a semaphore. A program segment that has not proven bug free, this completely be ruled out because that doesn't make any sense. A program segment that has causes unexpected system crashes, this also doesn't make any sense. Option D is correct. What is the critical section? Critical section is a section of piece of a code in a process. When executing, a shared memory will get accessed. This memory is not just doesn't belong to only this process. That memory will be shared by many of the other processes. So here is the memory is a shared resource. So understand carefully, what is the critical section? When the critical section is written, when the critical section is executing, some shared resources are being accessed. So what is the correct answer in this? Okay, a program segment where shared resources are accessed. As simple as this. Are we clear? Chakradhar? Or not? Can you go to the next question? You need to say, because we are running out of the time. We need to solve as many as possible. Okay, fine. I just take it as a S. Yeah. Consider the system with 3 processes that share 4 instances of same resource type. Each process can request a maximum of k instances. Resource instances can be requested and released only one at a time. Largest value of the k that will always avoid a deadlock is 1, 2, 3 and 4. Okay. So what is this? What is the answer for this? That is, there are 3 processes in the system and there are only 4 resources. So 4 instances of a resource. Each process can request a maximum of k instances. Okay. Resource instances can be requested and released only one at a time. What is the largest value of the k? Okay. So what is the answer for this? I'll tell you anyhow. How many processes? There are 3 processes, P1, P2 and P3. These can request a maximum of k resources, but the number of resources are very limited, which are equal to 4. What must be the value of k in order to avoid a deadlock? This is the question, right? Understand? In order to avoid a deadlock, the maximum resources that can be requested is only 2. So understand, there is a simple solution, practical solution for this. The system needs to have a sufficient number of resources in such a way that these resources must be able to fulfill at least one process complete request and a remaining process request minus 1. Each request minus 1. Okay. So there are 3 processes, at least one process must be completely given. So here, if k is equal to 2, 2 can completely be given, and the remaining process request minus 1, here 1 and 1. So 2 plus 1 plus 1 is actually equal to 4. So in order to avoid a deadlock, we need to have sufficient number of resources in such a way that at least one process resource request must be satisfied. All the other process requests respectively should be satisfied in such a way that their resource request minus 1. So if the total number of resources are equal to 2, then 1 will completely be satisfied, remaining 1 and 1. So the answer is equal to B, which is equal to 2. Okay. The next question. At a particular time of computation, the value of the counting semaphore is 7. Then 20 P operations on the 15 V operations were completed on this semaphore. What is the resulting value of the semaphore is the question. What is the resulting value of the semaphore? Counting semaphore value is equal to 7. Then what happens? 20 P operations and 15 V operations are performed. Then what is the value? The value is simple. P operation decrement the value of the semaphore. V operation will increment the value of the semaphore. Okay. 7 minus 20 is equal to minus 13 plus 15 is equal to 2. 7 minus 20, excuse me, it is B, sir. It is B, sir. What happens? See, you just gone somewhere. Are you here? Or in cloud 9? P operation will decrement the value of the semaphore. V operation will increment the value of semaphore. From where you go, you're getting 12. Initially 7 minus 13 is equal to, initially 7 minus 20 is equal to minus 13. Minus 13 plus 15 is equal to 2 only, right? So option 2 is the correct option. The next question. Each process, it's a one maybe some question which consumes some time, but we'll discuss this question. Each process Pi, where I is equal to 1 to 5, decoded as follows. Where I is equal to 1 to 10, for example. It is not 1 to 5, it is 1 to 10. Okay. Repeat P mutex, V mutex forever. Code for P10 is identical except it uses V mutex in the place of P mutex. What is the largest number of processes that can be inside the critical section at any moment? I will show you. You just need to be with me very quickly. Okay. So the thing is, the critical section must be protected by only a pair of P semaphore followed by V semaphore. P on mutex, V on mutex. Okay. You cannot use any other possible options. Initially, before you entering into the critical section, you need to perform P operation. After you leaving, you should perform V operation. Okay. So initial value of the semaphore will always be equal to 1. Okay. Now, how many processes are there? There are 10 processes. Okay. Now let us say this is the critical section. All the processes have actually been coded perfectly, but only one process is coded reversed. For one process, this critical section is protected by V followed by V. Okay. Atri Chaudhary, no. Critical section meaning. How to tell you this? You're not attending the OS classes, which I'm taking regularly these days. Critical section. There are, see, I don't know how to answer this because just altogether you just complicate this. But anyhow, I'll tell you. I'll take some time to explain you this. Let us say there are several processes P1, P2, P3, P4, P5. Okay, all these processes are a part of an application. For example, all these processes are a part of MS Word application. Okay, MS Word. This is the MS Word, a document application. P1, P2, P3, P4, P5. Generally, what happens? P1, P2, P3, P4, P5. These are the different processes, but are the part of the same application. Every process will have its own main memory space. But these P1, P2, P3, P4, P5, due to some convenience, they will have some common memory space. Okay, P1, it has its own memory region. P2 also it has its own memory region. P3, P4 and P5, all these having their own memory regions. But in addition to this, they also do have some memory region which is in common for them. But in order to access them, they will have a piece of code. In P1, there is a piece of code to execute to access this. P2 also has a specific piece of code. When executing, this memory gets accessed. That piece of code is called a critical section. I hope you got the point. Okay. That is what a critical section. Anyhow, in my regular ground zero series, I will talk more about this. So don't miss the classes which are happening at 5:30. Okay. So, okay. Now the thing is, D, none of the above. D is the correct option. Chakri is a correct option. I'll tell you why. Initially, let us say process P1 wants to enter into the critical section. Process P1 performs P mutex. When P performed on the mutex value will become 0. Then process P1 can enter. Did you get me? Now what can happen? Process 10 also can enter, because process 10 does not enter into the critical section by P of mutex. I will show you this. V on mutex, critical section, and V on mutex. This is the order of the process P10 to enter into the critical section. So process P10 can enter into the critical section by performing V on mutex, which again value of the mutex will be equal to 1. Now the current total number of processes will be P1 and P10. Now the thing is, as the mutex value is again equal to 1, that allows one more process, say P2, to enter into the critical section. So the value of this will again be equal to 0. Now what happens? Now when the process P10 wants to leave, it will perform V on mutex. If the V on mutex is performed, again it will be equal to 1. If this iterates, what will happen? The total number of processes can be inside the critical section. Simple. If any cooperative process critical section is being protected by V followed by V on a semaphore which is called mutex, then there is a possibility of all the cooperative processes to be in the critical section at the same time. So the number of processes that can enter into the critical section at this point is equal to 10, which is the maximum number of the process here. Did you get me? Here 1 is not correct, 2 is not correct, 3 is not correct. Rather, all the cooperative processes can enter inside the critical section at the same time. Okay, so D is the correct option. Okay, so we just crossing that. I just will have one more session on this synchronization, maybe on Monday or Tuesday. Did you understand so far everything? There are still a lot more. There are only, I guess, 4 more questions to discuss, I guess. Yeah, 3 more questions we'll discuss. Yes. Now the next question is, if every process enter only once, then answer is 3. Every process enters only for once, meaning, can you tell me that how many times that the shared memory will get accessed? There is no restriction. Okay, the shared memory can be accessed for n number of times. We don't know how the code is written, sir. Okay, so do not make any misinterpretations here, no misconceptions. If at least one of the cooperative process protected critical section with V followed by V, then that means that there is a possibility that all the cooperative process can be inside the critical section. Okay, now the thing is, the question number 6. Let me explain you this. The enter CS and the leave critical section function to implement critical section process are erased by test and set instructions. Okay, you might have heard about test and set lock. What is the test and set lock? Test and set lock is a hardware lock. Okay, to protect the critical section, even if there is a restriction, then it is 3. Yes, what you told is correct. Even if there is a restriction, let me go back and see if there is imposed a restriction. Initially, let us say P1 enters, P1 makes it 0, then P10 enters. Okay, so makes it 1. and then P2 enters, it makes it 0 again. Okay, now P10 leaves. When P10 leaves, it will be equal to, yeah, the what you told is correct. If there is a restriction on the number of times that a process can execute in the critical section, only that is only for once, then the maximum number of processes that can be inside the critical section is simultaneously equal to 3 at any point, at any stipulated point. What you told is right, but there is no such presumption can be made, right? But what your thought process is rightfully correct. Okay, now critical section can be protected by one hardware solution called test and set lock. Test and set lock is being provided by the CPU designers. But the problem with the test and set lock is test and set lock is going to satisfy only one criteria, that is the mutual exclusion. That means by using the test and set lock, we will be able to protect our critical sections, but this test and set lock doesn't support bounded waiting. Okay, only bounded waiting is not satisfied. When the bounded waiting is not satisfied, what's going to happen? Simple. Have a look at this. The above solution of this is the solution. The thing is, where is this? Yep. Critical section is protected by test and set lock, right? Above solution, meaning test and set lock to the critical section problem, is a deadlock free, starvation free. A process can enter in CS in FIFO order. More than one process can enter into the critical section at the same time. Definitely fourth one will be eliminated, because by using the test and set lock, mutex is guaranteed. When the mutex is guaranteed, only one process is allowed to be in the critical section. Next one is the process can enter into the CS in FIFO order. There is no possibility, because although there are 100 processes, there is no guarantee that those processes will execute in the 1 to 100 manner, 1 to 100 order. Whenever the process wants to enter into the critical section, and if it requests first, regardless of its order, regardless of its ID, it will be able to enter into the critical section. Here, it will not enter into the critical section in a FIFO order. Solution is a starvation free. It is not possible, because test and set lock. A paid student. Okay. Okay, not paid, but 5:30 we have a pre-app classes, right? You attended some of my pre-app classes, so do not miss 5:30 classes. 5:30 classes are absolutely free for everyone. Okay, starvation free. Starvation free cannot be guaranteed, because test and set lock doesn't guarantee the bounded waiting. If the bounded waiting is not guaranteed, then that means there is a starvation. Test and set lock cannot avoid starvation. Option 2 is not correct. Okay. Above solution to CS is a deadlock free. Yes, this is the only correct option. Starvation free cannot be guaranteed. FIFO order cannot be guaranteed. More than one process can enter into the critical section, cannot be guaranteed. Okay. Next one. The following two functions P1 and P2 that share a variable B with an initial value of 2 execute concurrently. P1 and P2. What is the number of distinct values that B can possibly take after the execution? Now here we just need to understand the question initially. There are two processes. One is P1, one more is followed by, one more is P2. When these two processes are executing concurrently, what is the value of the B? How many distinct values can be given to B? Because B is being updated simultaneously. Concurrency meaning what? Simultaneously it is being updated by both of the processes. B is a shared variable. Okay. Let us have a look at this. Now the thing is, let us execute P1 followed by P2 and then observe what is the value of B. Now initially C is equal to B with the initial value of 2. Okay. Now I would say B is equal to 2. C is equal to B minus 1. So what is C value? C value is equal to 1. B is equal to 2 into C. 2 into 1 is equal to 2. Okay. The value of the B is not altered or changed after executing P1. Now P2. When P2 is executing, Will the value of B get affected? Let us see. D is equal to 2 into B, meaning D is equal to 4. B is equal to D minus 1. Yes, D value is equal to 3. Did you get me? So B value can also be equal to 3. So far, two values have been taken. One is 2, one more is 3. The next one is concurrency, meaning we will try to execute first line of each statement. Yes, no progress and no bounded waiting leads to starvation. Absolutely. Absolutely. If there is no bounded waiting, if there is no progress, obviously there will definitely be starvation. Starvation will definitely be on the cards. Okay. In the corner waiting for you. Okay. Now, 2, 3 are the two possible values after you execute this simultaneous, one after another. Now you go for a concurrent execution. In the concurrent execution, so far B values are equal to 2 and 3. Concurrent execution meaning first B's first statement gets executed, P1's first statement gets executed, followed by P2's first statement, followed by P1's second statement, followed by P2's second statement. Let us see. C is equal to B minus 1. What is B minus 1? B minus 1 is equal to 2. Okay. And then D is equal to 2 into B. What is B? B is equal to B, initially 2, right? 2 into B is equal to 4. And then B is equal to 2 into C. What is C? 2 into C is equal to 4. Now, B has taken additional value. Initially, there were 2, 3. Now, one more value has actually been added, that is 4. Okay. And followed by B is equal to D minus 1. D minus 1 is equal to 3. So, the possible values that can be taken is, hi Shai Darshan, good evening. The possible values that can be taken by B is equal to 2, 3 and 4. The number of distinct values B can possibly take after the execution is 3 only. Okay. And the next question. Yeah. Okay. Yes, process synchronization. Consider two processes P1 and P2 accessing the shared variables X and Y protected by two binary semaphores Sx and Sy respectively. Both initialize to 1. P and V denote the usual semaphore operations, where P decrements the semaphore value and V increment the semaphore value. The pseudo code for P1 and P2 is as follows. Now, understand carefully. This is the critical section because X and Y are being accessed. Here also X and Y and X are being accessed. This is the critical section. Okay. In order to protect the critical section, they are using two semaphores. One is XY, Sx, and one more is Sy. Both are initialized to 1. Okay. Now the question is, before you enter into the critical section, there are two statements, but those two statements are actually empty. We need to fill these empty spaces to enter into the critical section. We will see what is the actual question. In order to avoid the deadlock, the correct operators at L1, L2, L3, L4 are respectively. I will tell you one simple shortcut to answer this question. The shortcut is, if you are using two semaphores to protect the critical section by more than one process, in order to avoid a deadlock, both of the processes should be able to perform the P operations and V operations in the same order. For example, okay, let us say this P1 before enters into the critical section, it perform the operations on the semaphores in this following manner. P of Sx followed by P of Sy. If P1, let us say, it performs the P operation in this order, then P2 should also follow the same order. If the order is reversed, then it will be a deadlock. I will show you directly the deadlock. Let us say in P2, what I have written is P on Sy followed by P on Sx. Now you can clearly see there is a deadlock, right? There is a deadlock clearly here. Because when P1 executes, it holds Sx semaphore. Sx semaphore will be equal to 0. Now then what happens? It got preempted, and P2 concurrently when it is executing, every process is expected to execute only the first statement. In such case, P1 executes only one statement, P of Sx. After P of Sx is executed, Sx is equal to 0. Now P1 holds Sx semaphore. Then P2 when executing, it holds Sy semaphore. It performs P on Sy. That means Sy also is equal to 0. Now P1 holds Sx, P2 holds Sy. When P1 returns, it will be blocked on Sy semaphore. P2 when comes back, it will be blocked on Sx semaphore. Simple. Because Sx is held by P1, Sy is held by P2. So whenever they come back, no matter in which order they comes back, they will get blocked on the semaphores because they actually are held by the other process. Okay. So this, in order to avoid a deadlock, what we need to do is, we need to perform in the same P operations on the same order, P of Sx followed by P of Sy. Here also P of Sx followed by P of Sy. So what is the option? Option is P of Sx, P of Sy, P of Sx, P of Sy. Yes, option D is correct, not C, sir. Chakradhar, it is not D, it is not C, it is D. P of Sx followed by P of Sy, again P of Sx followed by P of Sy. Option D is the correct option, with which we have come to an end of this session. I hope you understood to the level that I desire you. I hope you understood each and every topic that's been discussed here. Okay, so register to 2025-26 Vision Gate course. If you get registered to this now, I guarantee you that you are going to crack the GATE exam, especially when you belong to the computer science, because it's being completely led by myself, and in which you're just going to get this live classes, recorded classes, study material, practice quizzes and mock tests. So enroll now in order to make most out of it. Okay, so that's it from the session. Thank you so much. If you do have any more doubts, I just can wait for 5 more minutes. Otherwise, we are going to take a good night. Are we done? Chakradhar, Atreya, are we done? Like, share and subscribe to this session and the channel, and share this session to as many people as possible, because especially when they are actually aspiring the BARC exam, it will be helpful to them to crack operating systems. Yesterday, day before yesterday, I also have taken a COA, and please do share these sessions. And if you do not subscribe to this channel, I request you to subscribe to this immediately. So that's it from the session. Thank you so much. Anil Prasad Surampudi signing off.